this is all about the Claisen rearrangement, which is a rearrangement that we see with phenol uh, ethers that are made from phenol with an allo group on them. So what are we talking about? A phenol can be made to make an ether with an allo group. So we see it over here. And there's a special rearrangement that they all know. When you heat them up, they do a pure cyclic reaction in which the electrons move to attach to the end of the allyl group, and those electrons move to form a new location for the double bond, and then this forms a ketone. And then after this rearrangement occurs, the ketone does a tautomeric rearrangement to give you the aromaticity back. Let's look at this mechanism. So here we have the allyl ether, and notice the electrons move here, here, and here. And what we get is this ketone. Notice this hydrogen's out of place, and this is non-aromatic now. So what happens is this hydrogen, it was here to start with, but now this is preventing this from returning to aromaticity. So what happens is this ketone automerizes to become an enol, and that hydrogen right here moves to this oxygen, and the double bond moves down there, and aromaticity is restored. And it looks just like someone had cut off this group and moved it here. The only thing is that we've been able to look at where the carbon is with carbon-14 label. If we put a carbon-14 label right here and run this reaction, we find that carbon-14 label is attached to the ring. So we're still very confident that the way that we're showing this mechanism is true. So now what I'm going to have you do is try this on your own. What would happen if I took this allyl ether, you see this is an allyl ether right there, and do the Claisen rearrangement on it? What is the product? Pause it and try and figure it out, and then restart the lecture. Well, you can see what happens is this carbon becomes attached there. The double bond is gone and moves here. So look, there's this carbon, there's this carbon, and you see the double bond is now there. This bond's broken, and the proton that was here is now up here on the side, on this oxygen up there. So we've got some you try it problems here for you now. Go ahead and see if you can select the correct product of the reaction of this alkene with MCPPA, and then cleavage of the epoxide with hydrobromic acid. Okay, if we look at this, we will put an epoxide here. Now when we treat it with hydrobromic acid, we look to see we've got secondary here, tertiary here. So we know the bromide is going to be attached to the tertiary carbon. So if I look around, the bromide's attached to the tertiary carbon there, but we don't have the alcohol group over here. MCPPA would make this compound, but the hydrobromic acid would cleave it. This compound wouldn't happen because the bromide is going to want to go to the tertiary carbon. This won't happen unless you treat it with, let's say, aqueous hydroxide, you would get this. Or if you treat it with aqueous acid, you'd have to have a lot of water in there. This would form. But what's going to form when it's just hydrobromic acid and no water is the bromide is going to be attached to the tertiary carbon, and the alcohol is going to be on the remaining carbon. So this is the correct product. What is the major organic product of this reaction? Well, when we look at this reaction, we see we've got a Grignard reagent, which is basic. Basic compounds do SN2 to epoxide. That means it's going to attack at this carbon. So let's look to see where we get attack at that carbon. This means we're going to have 4 carbons, and it's going to be carbon, 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 carbon. This doesn't fit this. This would mean we had attack on the more hindered carbon. This doesn't make sense at all, because if you had attack on the more hindered carbon, the ring would open. This is a free ring open. Well, this wouldn't happen. There's too many carbons there. Okay? This is this carbon, and so you can only have 1 carbon on that chain. We got too many carbons. Let's look at this one. That's just the methyl group coming in and the ring not opening, so that won't happen. And if I look at this one, I can see here is the methyl group that came in, and then the ring opened to get the hydroxyl, and this is the carbon that was right there. So this is the correct product. So what is the product of the Claisen rearrangement of this allyl ether? Well, when I look at this, the carbon that's going to get attached to the ring is going to be this one right there. And that's going to break. We're going to make that. That means there's going to be a methyl group on the carbon that is attached to the ring. And this double bond will be gone and over here. Let's go through and look. Well, when the carbon moves over here, you're going to have, since it's going to attach here, the carbon that moves to here is going to have 2 carbons on it. That only has 1 carbon. So that doesn't work. This carbon has 2 carbons on it, but we're going to expect to see a double bond not attached here, but 1 carbon away. And again, double bond not here, but 1 carbon away. Again, double bond not here, but 1 carbon away. Oh, this one looks right. Here, we've got this methyl group, that's it. This carbon is this one. And then the double bond is going to move 1 carbon away, right down there. So this is the correct product. Z2-butene, okay, that means it is cis, reacts with bromine and water, followed by methoxide and methanol to form a product. What is the product of that reaction? So we're talking about cis-2-butene reacting with bromine and water that forms a halohydrin, then followed by methoxide, which is a strong base. It's a ring. So what do we get? Of course, we're going to form an epoxide. That's the only option we have here. The methoxide just acts as a strong base to cause ring closure to occur. When that occurs, what's going to happen? You're going to have the 2 methyl groups on the same side, because it was cis beforehand. It has to be cis afterwards. So the only one that forms is number 3.